All right. Good morning. How's everyone doing? Okay. So, any questions before we start? Just by show of hands, how many of you are, following what's going on with the back propagation? Is there anyone here? You're okay with what we're doing? Anyone here who has just doesn't think they are really grasping the whole thing? Anyone? Okay. I mean, if there is any question, please come during the office hours and I can go through it in quite detail. I mean, we are going through this in pretty much the most in the finest possible detail we can. But if there are still questions, definitely you can come back. I haven't seen a lot of activity on Piazza regarding programming assignment 1. So either you're all killing it or you haven't started. But please remember there are only 28 days in February, which means that you have around 2 weeks for the assignment. And so please get started if you haven't. If you have done it, that's fantastic. Yes, go ahead. It's going to be released today. Yeah, so we apologize. That was uh, so what happened was, since this TensorFlow is a new library, it didn't run on Metallica. So we ended up creating another server called Springsteen, and we installed TensorFlow on that, but then it had some other things missing, and so the whole thing didn't run quite as I wanted it to. But I think today it will be fine, and then you can start playing with it. That wouldn't take you too long in terms of doing things. It would take long in running it, but it wouldn't take. There's no implementation there, just sort of analysis and seeing what happens, right? Okay, so if there are no questions, let's continue with our backpropagation. So I'm going to go a little fast today. I think I went in quite detail last time, but we did not cover the whole thing, right? So what we were trying to do, and let me switch here, last time, was that we were trying to compute the partial derivative of our objective function, right? And our objective function, if you remember, looked like this, right? So it's a what we call a squared loss function, where all you're doing is you're computing the difference between what you predict or what comes out of the output units, right, and what the actual label is, and you just square it and sum it up, right? In the assignment, there's a different form of this function, but the idea is that you have some objective function. You want to apply gradient descent because you want to estimate the weights, right? So what we do is we compute the partial derivative of this objective function with respect to every weight entry that you have. So remember, switching back here, that in a neural network, I want to go to the whole thing, right? So you have many hidden layers, you have many output layers. Each hidden layer has a bunch of units. Each unit has a vector, right? And in each vector there is a weight element. So we want to compute the partial derivative of that j, which is computed over here, calculated over here, with respect to every weight that's inside every unit, right? And what we did last time was we were able to sort of do this for the output units, because the output is slightly easier because the output unit weights contribute directly to your O's, which get connected to your which are used in your J, right? So it's a direct function. But then we saw that the weights over here are not directly connected, right? So if you remember, the weights here take your inputs, combine them, and then do a sigmoid on that, and then send it forward, and they get sent to every output unit, which means that the impact of a weight entry inside here is on each one of these, right? So when you want to compute the partial derivative, which means that you have to do some kind of a what do you call that, a chain rule, right? So this is a function of that is a function of that, right? So you want to figure out what each weight entry goes into, right? So we made this observation number 3, so I'll jump to that, which is that the net j is the output, is the sum of weight times inputs that's coming out of every neural unit in the hidden layer, is connected to the final j through all output nodes. That's what I said, right? So which means that if you want to compute this value, the partial derivative of j with respect to any net j, right, that will be a summation over everything, over all output units, because the j is connected to net L's, right? The net L is what is coming out of your output units before the sigmoid. So this is how they're connected. So you do this chain rule and then you open it up. Once you compute this value, then you can compute the partial derivative of j with respect to your weight entries, because that was a result that we saw earlier here. So for any weight entry, the partial derivative, this is what we want, right? And this can be split into whatever is the input coming into that weight entry times the partial derivative of j with respect to the net value. And then that coupled with the result that I just told you, we can now compute the whole partial derivative. So let's go here. All right, we are, today is what, 24, 5. Okay, so here, so we have this result, and then we had the observation number 3. Observation 3 is that the d of net j, which is the output within the jth hidden unit, right, is equal to this is a simple fraction rule, but since there are k of these and net L, so we go L equal to 1 through k, right? So this is how we will compute this. And then once we have done this, then we can say that the partial derivative of j with respect to the jth unit, and within the jth unit, the what, p the pth element, right? So we are using that notation. So this is, we are talking about the jth hidden unit. In that there are p plus 1 vectors, right? P plus 1 elements. So this will be equal to, we use this and this, we combine these two, so it will be, let me write this part first, times whatever the input is coming into the pth element. Now what the input that is coming to the pth element of the jth neural unit will be xp, right? Because that's the pth weight. So if you remember in our neural network architecture, right, so if these are my hidden units, each one of them has a vector here, and they're all getting these, sorry, is x1 x2 through this, right? So that's the input that is coming to this, that's xp, and that gets multiplied with our this whole thing. So let's quickly see how to do that part. Right, okay, so now what we are going to do is try to see how can we compute these things over here, right? Now this we already did last time. This is, in fact, it is right here, right? This is the partial derivative of j with respect to the net in an output unit. This is just for that error function, it is yl minus ol. Okay, so this is good, so we can switch that here. Now let's see what is this part. Now this is L equal to 1 through k. So what is net of L with respect to net of j? Any questions so far? Okay, good. Right, so now you can break this. Now remember, what is this, the relationship between net L and net j, right? So there is this jth hidden unit wj, and there is a jth lth output unit. So this is output unit and this is hidden unit, right? So what happens here is that there is a net L being produced, or net j, and that is being transformed into sigmoid of net j coming out here, and that is going in here, and that's being combined to compute your net of L. Right, so that is sort of the chain. So if you want to compute this partial derivative, all you do is you sort of work backwards from that. So if you look at the class notes, you'll sort of see that I'm going to wing it a little bit. Whew. Right. Right. So just for our notational simplicity, just for this time, okay, I'm going to call this. So let sigma of net j, which is the sigmoid of net j, be denoted as a of j, just for a z of j, just for so that I don't have to write it over and over again. So you can write this now as j, net L over zj. Yeah. All right. Now what you can see is that when this zj or this zj equal to this thing goes into the output unit, it gets combined with the weight vectors, right? So only one of them will contribute to the net of L. So you can write, there are two parts that we want to compute. So this part will actually just be W times the jth entry in the Lth vector, right? So this is going to this vector over here, and only the jth entry here will contribute to this, will take this value, right? So when you expand, I'm not expanding it, but essentially if you expand this whole thing, right? In fact, let's do that. So remember that net of L, right, is nothing but summation over j equal to 1 through whatever number of hidden units we have, let's say m, right, times W Lj times zj, right? So whatever is coming inside, we are just adding it up, right? So when I compute the partial derivative of this with respect to zj, only one of them will survive, and only this one will be left there, right? So that is this, and this is easy, right? This is just because remember zj is nothing but sigmoid of net of L, and last time we saw that partial derivative of that. See, zj is sigmoid of net of j. Sorry, this is going to be j, right? So implies that the partial derivative of zj with respect to net of j is essentially zj1 minus zj. That's a property of the whole thing, right? Of the sigmoid function. So this will, you can write this as just the output coming out of this, so zj1 minus zj, and later you can replace it with sigmoid of net j. So this is one result that we got. This is result number second. So now we can plug all of them here and then say that is summation, this gets replaced by this, minus yl minus ol times, so this is L equal to 1 through k, where is this here, WLJ ZJ 1 minus ZJ, the whole thing, right? Of course you can always pull this out because this is not depending on L at all, so then you can say that this is, you can rearrange it, right? But the idea is that now you know how to compute the partial derivative with respect to any weight entry in the hidden unit as well, because you know what this is. This is the true label, this is the output that you got at the end, this is the weight, current weight at that entry, also at the corresponding output entry, and this is the output that is coming out of the jth hidden unit. So we have everything, so you can compute that, right? So this is what you have to do in the programming assignment as well, is essentially encode the implement these things. Okay, any questions so far? Oh yeah, go ahead. Oh right, oh I'm sorry, so that was over here, right? Yeah, so I have to keep an xp over here as well. which also can be outside the summation. Yes. Right. Yes, so a good question. So the question is, if we add more hidden units, how do we compute the backpropagation there? And that is the reason why I sort of began with this general approach of for any unit. So essentially, you have to do longer and longer chain. But what happens is that if you look at this, in fact, that's part I skipped, is that if you, where is it? Right. You can call this part, which is zj1 minus zj times the summation, right? And this is actually the delta L that I talked last time, right? We defined this as a delta L. So you can write this whole thing as delta L W L J, L equal to 1 through K. So this is essentially here, right? So all you're doing here now is you're saying, right? So then this dj over dwjp becomes minus delta this. So I'm going to call this delta L. I'm just defining this term. So delta L times xp, I think that's what it is. So delta j, I should call it j. This is for the jth unit. So you can actually write your partial derivative. I mean, this is nothing but just rearranging and redefining, I mean, defining the terms in some way. But what you will see, you'll see an interesting pattern, which is when you computed the partial derivative for the output units, right? We wrote it like this. So there's some delta L that we are computing, and the partial derivative is just delta L times the input. And then even here you will see the same thing. It is, you're computing some delta J, and that's the input, right? So if you look at this carefully, all you're doing is you're propagating your errors back. You had some error in the at the output unit delta, which is over here, and the partial derivative was just a function of that delta L, right? And then you jumped to your hidden layer, and there also you had delta J, and the partial derivative was with respect to that. So if you have another layer here, what you will see is that it just sort of jumps back. It has a similar pattern. So it won't be too much of, I mean, if you do it carefully and with following this kind of pattern, what you will see is it will be easy to derive. It won't be that cumbersome. The only thing is, of course, if you have another layer, then the input to the middle layer will not be the x's, but whatever is coming from the previous layer, right? So just, if you do it carefully, you will be able to sort of do it for any number of j's, but just becomes, a little more messier at the very end, right? And that's why, I mean, for the assignment, of course, I want you to implement it, but in practice, it will be better to just use a library. Yes, go ahead. The notes here, or right? I'm just using it again. I might have. Mm. Oh, right. Did I write it wrong? So here, no. So when I computed dj over net of L, it was not this. You're right. It is. There was one more term here. Right. You're right. Yeah, I made a mistake there. So this should be not just this much. This should be. Right. So this is okay. Actually, what I should say is that this is just minus delta L, which is YL minus, it has a whole thing. Yeah, you're right. So I made a mistake here. It's just it's going to be this. This is just from the previous result. I forgot to add more here. So it is just negative of delta L, right? That makes sense? So then you have to be carefully replace that over here. So instead of just doing YL minus WL, maybe I should just write delta L here, right? Delta L, right? And that's it. After that, this should be fine. Yeah, that makes sense. All right. Yeah. Apologies. This is so messy. I always make a mistake. Any other questions? I mean, of course, if don't go by this sort of discussion. This is just so that you get a feel. But in the handouts, I have more detailed step-by-step derivations. All right, very nice. So essentially what we have done now is now we know how to train our neural network, because we can now compute the partial derivative of our error function, objective function, with respect to every weight entry, right? Which means that now we can feed the partial derivative. So what we typically do is we take all of our partial derivatives, create a very long vector, right? As long as how many number of weights you have in all of your units. And you stick it into this long vector, that becomes your gradient, the gradient of the j with respect to all of your weights. And then we feed it to the gradient descent, right? So we start with some w's, we go forward, then we come back, then we compute our gradient, and then we subtract the weight minus eta times the gradient, and then we keep doing that until we converge. So essentially this is the whole backpropagation algorithm. Any questions so far? Okay, so now I'm assuming that we all know how neural networks work. I mean, how they work during prediction and how they work during the training. So after this, what I want to do is just sort of talk more about neural networks, just a general discussion, no derivations anymore. Whew. All right, so this is the general algorithm that you know already. Okay, now there are some questions about neural networks, right? So one thing, of course, is that the error function, right? Error function is not really convex, okay? Like in perceptron, I was talking that when gradient descent is guaranteed to converge if the function is convex or concave in this sense, right? So if you want to find a minima, and if your function looks like this, then wherever you start, you will always reach the bottom. That is fine. But this objective function that we are dealing with, right, because it is a function of so many weights, right? It's no longer a function of x and y, it's a function of many weights. So there is no guarantee that it will be convex in all of them, right? So it might have some local minima as well, which means that there is no guarantee of convergence with these kind of methods, right? It won't converge to the right and the optimal value all the time. So there are some tricks people sort of apply to improve the backpropagation algorithm, right? One of the things people do is, of course, stochastic gradient descent that I discussed very briefly last time, which is that instead of computing your error function with respect to all of your training data, you do one training data at a time, right? So you take one training data point, and then you adjust your weights until you converge. And then you take the next training data point and next training data point. So that way, it has been studied that algorithm has a little more robust convergence properties than just simple batch gradient descent. Okay. The other thing is that another aspect that I didn't talk about is this notion of adding momentum. So this is another idea where what you do is that as you are updating your weights, right, you do not update your weights according to the gradient just using that equation. Instead of that, you take an average. So the notion of adding momentum is that in general, this is how you work, right? Your new W is W minus eta times the derivative of your J with respect to whatever your weights are, right? But in momentum, what you do is you say that my new W is, we call this like W prime, and then new W is W prime plus, so alpha W prime plus 1 minus alpha W, alpha between 0 and 1, right? So what this means is that you're not simply following the gradient, but you are adding some momentum, in the sense that whatever you have learned so far, you want to not move away from that too much. So you want to stick to that little bit, but you also want to learn from the gradient. So you want to do both. So that is why you have this alpha parameter, which essentially takes a weighted average of where you are right now and where the gradient wants you to go next. Okay, so that is the notion of adding momentum. This actually works much better with stochastic gradient descent, because remember, stochastic gradient descent, you are looking at one data point at a time, right? So maybe you got one data point, you adjusted your weight so that it does very well on this data point. Now you got another data point, right? Now if the other data point is erroneous, right, if it has some error in the data itself, or maybe the label is flipped for some reason, then you do not want your weights to suddenly change to adjust to this new data point, right? So what you do is you have this notion of momentum, where you do not move, you do not follow the gradient blindly. You first say, okay, I'm here and I will only budge from here if there is a good reason, if the gradient is really helping me, is really telling me to move. Okay, so that is another idea. Another way to handle this notion of multiple minima or multiple local minima is, of course, that's easy, right? You run it many times. You run it many times with different initialization points, and hopefully you'll be lucky. One of the times you will reach the global minima, and then you can compare all of your solutions and take the one with the lowest value, right? So that is a typical trick in any optimization methodology. Any questions so far? Okay, very nice. All right, but the important thing that I want to talk about today, and it is a general machine learning concept, but I'm going to talk about it with respect to neural networks, right? So whenever you pick up machine learning papers, you will see some terms come across, a few terms, right? So you'll see terms like overfitting. You will see bias variance trade-off. You will see regularization as a solution to prevent overfitting. And then you'll also see this notion of principle of Occam's razor. So I'm going to talk all of this through an example, right? So let's do this simple experiment. So if you go to the course website, you will see a new notebook there. It's called if you go to part 5 notebooks, so there's a notebook called neural network demo. All right, so let me open it from here. What is this? All right, neural network demo. Okay, so too big. All right, so let's look at this. So I conducted a very simple experiment just to bring home this point. All right. So what the first thing I did was I created some data. Right. So whenever you have to do experiment, you have to create some data. Right. The way I created this data was I took a box, 2D box, and I sampled points uniformly from this box. Okay. Then I drew a line, arbitrary line, and then I called everything that was on one side of the box or line positive class and one other side negative, right? I also removed points that are within that are very close to the lines to create a very nice data set. All right, and then what I did was I flipped some labels just to add some noise to the data. So this is what the data looks like. So if you run this cell, sorry, this is what it looks like. This is just, I mean, every time it will be slightly different, but this is essentially, these are data points in two-dimensional space, right? and blue means class 1, red means the other class. This is the line that kind of differentiates them. I also removed some points just to make a very clean data set. So this is very clean, right? If I give it to any person, human, they will say, okay, yeah, I can sort of draw this line over like this, and that should do pretty well, even though there are some noisy points, right? And in fact, when you try this at home, you can play around with the noisy points by number of noisy points by saying instead of 100 I need 10, so then there'll be only 10 there, but just right. So this is tunable, but this is, I would say, typical data sets might look like this, real data sets. Of course, real data sets would not be in a two-dimensional space, so this is still very simple, but with some realistic noise added to that, right? Now if I feed this to a neural network, this whole data set for training, it will learn this line because this data is very clean. Even if I feed this to perceptron, it will learn this line as well, right? But that is not what happens in real life, right? This is all of your data. In real life, what you would have is some sample from this true data set as your data, as your training data, right? With labels attached to this. So this is what is available to you for training. And from this, you want to learn the surface, which in this case, of course, is this line, so that it can differentiate between the points, right? So let's see how we do that. Any questions so far? This is fairly straightforward, right? All right. So now what I do is I train a neural network classifier. Now here I'm using sklearn, the scikit-learn library in Python. They have a neural network implementation. You should not use that for the assignment, by the way. But essentially it has the same functionality as what you are coming up with, right? So it has logistic unit, right? Actually, you can change it to others as well. There is no momentum right now. I'm not using it, and I'm using two hidden layers here, both with 100 units each, right? And then I sort of train it. It doesn't run. Oh, sorry. There's a plotting function that I had. Okay, so now first let's look at this part, not look at the other part, right? So this is the boundary, all right? So this is the boundary that is learned by my neural network by using this training data, right? So the way I plot the boundary is pretty simple, but this is something that you should know as well, is, see, if it is a line, you can draw the line in Python, right? But if it is non-linear, then how do you draw it? The way to draw that is that you essentially sample this entire grid. You take points from, like, you divide it into very fine sort of a mesh, and then you take each point and you apply your neural net or whatever function you have on that point, and it will give you +1 or -1, and then you color it based on that color, right? So that gives you the set. Okay, so now let's look at this boundary. So what this boundary tells us is very interesting things, right? First of all, it is not a line, even though it should have learned the line, but what it does is it tries to minimize the number of errors on this data set, okay, by learning all kinds of weird structures in the middle. In fact, sometimes it depends on how the data is sampled. Sometimes you get even more interesting, not this one. Let's see. Okay, well, we'll stick to this, right? So essentially what it is trying to do is it is trying to minimize the error. That means it is trying to learn surfaces so that it puts most of the blue in blue and most of the red in red, right? That is the idea. I don't know why it's not working. Yesterday it was working beautifully. Oh, yeah, there it is. So what you'll see is it learns all these very complex boundaries, right? So that it minimizes. On the top, it actually tells you how many mistakes it made, right? So it only, on the training data, so it only made 4 mistakes on this training data set, right? However, when you apply this on the whole data set, which is the real data set, right, this is what it will do, right? It will basically put, it's the same boundary, but what you see here is that it makes many more mistakes, all right? In fact, it made 96 mistakes. I do not include the flipped points as mistakes because they're obviously on the other side, but On this data, on the true training data, it made many mistakes. So this is what we call poor generalizability. All right. So the algorithm was able to fit the training data very well. So this is what we call overfitting, because it really learned very complex boundaries to do that, but it was not able to generalize to real data set, right? And the reason for that is because it was only given a partial view of your data, right? If I had given this whole thing, then it would have perfectly learned the thing, right? So this is the problem of overfitting, and this is what we call poor generalization, right? And in machine learning, this is what we want to avoid. We want to have good generalizability. We want this algorithm to do well on unseen test data, not on training data. That we already know what the labels are, right? We want it to do very well on your test data, right? So how do we control that? How do we tell the algorithm, don't overfit, right? And that is what we call regularization in machine learning. That's a term we use to make sure that your algorithm does not overfit. Okay, so I'll give you an example here. So here what I do now is I use the same neural network, right? 100, but I change one parameter here. It's called alpha. I set it to 0.1. Earlier it was close to 0. It was right. So it was close to 0. Here I set it to 0.1. This is the parameter that controls the regularization. I'll come to what the regularization actually does. But this is kind of what we, in the assignment, I think it's called lambda. But this is the regularization parameter, which basically, so think of it as a knob, right? So when you turn the knob, you're telling the algorithm to not overfit the data too much, right? So if you do that, then this is what you get. You get a, okay, so on the training data, this is the line that you get, right? And this makes more mistakes than before, right? Earlier, that overfitted one made only 4 mistakes in a training data. This one makes more mistakes on your test data, but actually it does not make any mistakes on your, oh sorry, it makes 11 mistakes on your training data, but it makes no mistakes on your test data. Now remember, I do not count these as mistakes, the one that I have manually flipped. I mean, ideally it would have made these 100 mistakes, but those were wrongly labeled data points, right? But otherwise it does a perfect job, right? Just by changing this regularization parameter. When you go home and when you try this example, I want you to try other things as well. For example, if you only use one hidden layer, right? You make your model even simpler, even then you will learn a simpler boundary. So the general idea is that as you make your model more and more complex by adding more hidden layers or adding more hidden units per layer, you will tend to learn boundaries like this. Okay, but if you want to control it, there are 2 ways to do that. One is you keep a simple model, right? You just take 2 layers, 1 hidden layer, maybe 5 hidden units and so on, right? But let's say you don't know how to do that, right? So the other way to do that would be to have a complex model but regularize it, make it more regular in that sense, which will have the same effect. It will give you simpler model, right? So the idea behind a good machine learning model is that it should be able to accommodate some mistakes on training data. It's fine, but it should be such that it makes fewer mistakes on your test data. All right, so that's called generalization. So that knob, what essentially that knob does is that it strides this spectrum which we call bias variance trade-off curve, right? So on one side of your machine learning algorithms are algorithms that do not learn anything from your training data. Okay, so they, in the context of neural network, those would be in which all the weights are 0 except for the bias term, right? Which means the effect of x, the input, will be nothing. This will give the same answer every time, right? So if you run that kind of model here, it will just paint everything red or blue depending on what your equality clause is, right? Which is not a good model. So this model has no variance, a high bias, right? It is a model that before training it already knew what needs to be done. And on this side is a model which would follow the training data perfectly, right? So that would have a very high variance. The reason we call it high variance is because if you change the data, it will change a lot, right? So it varies with the data a lot. So high variance, high bias. Where you want to be is somewhere here in the good zone, right? So some bias, some variance, and the way to get there is by tuning this regularization parameter. All right. Now, in different machine learning algorithms, there are different ways to control the regularization. Okay. In the context of neural networks, the way we do it, and the way this algorithm would have done it inside, is by changing our objective function a little bit, and you will see that in your assignment as well. Is that instead of the usual j that we have seen, we add this other term as well. Now, what this other term does is, so if you look at it carefully, all it is doing is it is summing up the square values of all your weights. It's just adding them up, right? So on one side you have your error on your training data, which is j. On other side, it is how large your numbers are in your weights, right? And the idea is that you control between the two using this regularization parameter. So here I'm calling it lambda. In the sklearn library, they call it alpha, right? But it's the same thing, right? So the idea is that if you make your alpha to 0 or lambda to 0, then you are just looking at this, right? That means you're chasing that, you're overfitting. You're only concerned with minimizing the mistakes on your training data. If you set this to be very high, then what will happen is that it will try to get models which have very low weights, because otherwise this penalty will be too high, right? So it's sort of a juggling act. Okay, so this is how we control the bias variance. So if you look at our simple experiment that we did earlier, here I typed the sum of weights, right? So for this heavily regularized model, the sum of weights was 262, and for the unregularized model, the sum of weight was 20,000, right? So basically, the algorithm that had larger weights will overfit, all right? And I'll come to why that happens. But the idea is that this is why in neural networks, we use this as our regularization function. We try to lower the weights, right? The reason we try to lower the weights is because if you think about it, right? So what is the impact of weight? You have some x's coming in, and you have these weight vector, they get combined. If these weight vectors are high, then if this x changes a little bit, the change in the output will be large, right? Because this weight vector is very high. But if this weight vector is low, then the change will be lower, right? So it is less sensitive to change in the data if the weights are lower. That's why we try to keep the weights as not as low as possible. We try to keep the weights low while also trying to minimize our error, right? So we want to do both, right? But the question that I know is in some of your minds is that how do we specify this, right? How do we find this lambda? Where do we settle in this bias variance curve, right? And the answer is that there is no good way. So you have to do this just through trial and experiment, right? So you have some training data, some validation data that you have. You choose some value of lambda. You try your learning, see what is the performance on your validation data, right? And that way you can understand what is the impact of lambda on the performance. And then you choose the one that sort of you like. Any questions? Yes. Right. So the question is, why is there n here? Now, n here is the number of data points, right? Ah, that's a good point. I don't know why I have n here. Do I have n in the j? I mean, it won't matter much. That's not a C. Yeah, we don't have n here, right? I have to check with the t. I mean, so the thing is that this is just a constant anyway, right? What might happen is that you might have to play with larger values of lambda to see the difference. But I think I'll get back to you. I think we need to. I mean, ideally, if you keep both j and this regularized part at same scale, then your lambdas would be between 0 and 1. So it's easier to sort of play around with those values, right? But if this takes a very large value and this takes a small value, then you need to play with larger values of lambda. I mean, it doesn't matter really, but it's just that the scale of lambda would change based on the relative scales of these two numbers. So I don't know which one. Uh, What happens in the assignment I have to figure out. We have an n, right? And n is the number of data points, right? Right. And on j we don't have n, right? We don't compute. Oh, okay. 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 Yeah. Right. Yeah, there's no reason to do that. I think the only reason I think we are doing it is so that then these values, the scale of these values, would be close to what the scale of these values is. Then you can just vary your lambda from, I think, 0 to 1 or 0 to 5 or something, right? But if we do not divide it by n, then this whole number will be pretty large. So then you will have to have a very small lambda, I'm guessing. I mean, it's just about the scale. I'll check with the T's and get back to you on that. But I mean, it doesn't change anything really, because these are just constants. You could put anything here, right? You can put 2 times 10, 2 times 50. So the algorithm won't change. It's just that the value of lambda, the scale at which you want to play around with, would be different. So I'll get back to you on that one. Any other questions? All right. Yes. The lambda value does not depend on number of hidden layers really, because it's just a constant, right? It's you can set it to anything. The idea is that this lambda will sort of control how much is the impact of overfitting, right? So if you have more hidden layers, you will have more terms in this summation. You'll have another term here, the third layer, right? So you might have to adjust your lambda accordingly, but that is just to handle the relative scale, right? So let's say this j value is in the order of thousands, right? And this whole summation is order of 1, right? So 1000 plus 1, even if you set lambda to be 1 or 2 or 3, it would not really have an impact. It will still be towards overfitting side. So you'll have to set the lambda to very large values, right? So that is the only thing. I think those questions are related. There's the value of lambda needs to control the impact of either of these, but it also needs to sort of be in the scale that brings both of them to the same scale, right? Yeah. All right. Any other questions? Okay. So you know what? So this is end of 4th week, right? So in the syllabus we had one more part, 6th part in this one, but I don't think we'll have time to do that. I think we'll move to part B. So we have concluded basics of machine learning, and now we'll move to some more interesting parts in machine learning next week. But if there are any questions, just post them, and then I can answer those. But next class I will not talk about this at all, right? It'll be a pretty big shift. Any other questions? Okay, all right. Please get started on your assignments, and I'll see you on Monday. Thank you very much.